Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we'll be looking at another example with reaction. And our goal would be that you could solve the material balances. And in this case, we will be doing material balances for multiple reactions. Our example here, the problem statement says, a bioreactor is used for the anaerobic fermentation of grain. Glucose is digested by yeast to form ethanol and propionic acid by these two reactions. In a batch process, a tank is charged with 4,000 kilograms of a 12% solution of glucose in water. After fermentation, 120 kilograms of CO2 are produced and 90 kilograms of unreacted glucose remain in the broth. We want to know what are the mass percents of ethanol and propionic acid in the broth at the end of the fermentation. Now we can work in either mass or mole. It is easier to measure mass, but it's easier to work with mole. So step one that I choose would be to convert my masses to moles. Initially, I have 4,000 times 0.12 kilograms of glucose with 4,000 times 0.88, the balance, water. And that tells me my mass, but I need to divide by the molecular weight in order to turn this into moles. So I have 2.665 kilomoles of glucose, and I have 195.3 kilomoles of water in the feed. At the end, I'm going to have a combination of the glucose and water, but also I'm going to have the ethanol and the propionic acid and CO2. And so how much of each of those? Well, I have extensive reaction that I choose to use, and naming the first reaction that produces the ethanol and CO2 as reaction 1, and the second reaction that produces the propionic acid and water as 2, what I end up with is I started with glucose 2.665 kilomoles, and I lose this in reaction 1 and 2 with a stoichiometric coefficient of 1. For the water, I started out with 195.3, and I add 2 moles for each time reaction 1 or reaction 2 occurs. So plus 2x2. For the ethanol is next, and I start with 0, but I add 2 for reaction 1. Propionic acid, I add 2 in reaction 2, and for CO2, I'm adding 2 for reaction 1. So I can use this along with the given information that there were 90 kilograms of glucose remaining at the end. So this first piece is 90 kilograms dividing by the molecular weight. 180 gives 0.5 for my number of moles of glucose at the end. And I can use this along with the fact that I have 120 kilograms of CO2 remaining at the end. The molecular weight of CO2 is 44, and so this is 2.727. So I can combine these. If I use the CO2 equation, I get that x1 is 1.364. And x2, therefore, solving the glucose equation, is going to be 0.801. If we look at a data summary in either mass or moles, we were given this information that is currently on the screen in mass, and we've divided those numbers by molecular weight to get the number of moles. I now know that x1 is 1.364 and x2 is 0.801. And based on that, I found that the number of moles is 198, 2.728, and 1.602. And the mass is 3549, 125.6, excuse me, and 115.4. If you wanted this in mass percent, dividing by 4,000, I have 2.3% glucose, 88.7% water, 3.1% ethanol, 2.9% propionic acid, and 3.0% CO2. There appears to be a little bit of round off, but anyway, you see that we've got our basic calculations. This concludes this example. Thank you very much for your time.